Hello, I'm Sam, and I'm a PhD student at Balliol College studying maths. And today I would like to talk to you about groups of symmetries. Let's start with a fun example. How many permutations are there of the Rubik's Cube? That is, how many ways are there of mixing up the small cubes by performing sequences of twists of the faces of the Rubik's Cube? And the answer is this gigantic number. So where is this number coming from? Is it just some big random number, or is there some sort of mathematical structure that underpins it? Well, one thing we can do is factorize it, and it turns out this can be factorized like this. Okay, so now it looks like there is a bit more structure going on to this number. We've got some powers of 2, some powers of 3, some factorials getting in on the act. You might also notice that 8 is the number of vertices of a cube, and 12 is the number of edges of a cube. So maybe there's some mysterious significance to this. And indeed, there is a mathematical structure that underpins the permutations of the Rubik's Cube. And these sorts of structures are known as groups of symmetries. Okay, let's start with some basic definitions and examples. What are symmetries? A symmetry is a way of moving a shape so that it lines up with its original position. For example, you can rotate a square by a quarter turn clockwise in that case, or you could reflect it about the horizontal axis, say. And we also need to add the following to the definition. We consider two symmetries to be the same if they move each point to the same place. So, for example, rotation by a quarter turn clockwise is the same as rotation by a 3/4 turn anti-clockwise. Or if you like, we only care about the end result of a symmetry. We don't care about the specific movements used to get there. Otherwise, there would be far too many symmetries to consider if we cared about the specific movements. So what are the symmetries of the square? Well, it's not hard to count them. There are 8 of them. These are 4 rotations, including the 0-turn rotation, which also has the fancy name identity. In fact, this is a general name. For any shape, the symmetry which doesn't move anything is known as the identity. And then there are also 4 reflections of the square, reflecting about the horizontal axis, the vertical axis, and 2 about diagonal axes. Now, an important feature about symmetries is that they can be combined. Any 2 symmetries can be combined to produce a third symmetry. For example, rotating by a quarter turn clockwise and then rotating by a half turn clockwise is equal to rotating by a 3/4 turn clockwise. Or a slightly more involved example, reflecting in the vertical axis, then rotating by a half turn is equal to reflecting in the horizontal axis. Let's see why this is. In order to keep track of these symmetries, I've decorated the square with the letter F. Let's see what happens. So we want to first reflect in the vertical axis, then rotate by a half turn, and we see that the letter F is upside down, as if we had just done a single reflection in the horizontal axis. Any symmetry can also be performed in reverse, and this is called the inverse of a symmetry. For example, the inverse of rotating by a quarter turn clockwise is rotating by a quarter turn anti-clockwise, and the inverse of a reflection is itself. because if you sort of perform a reflection twice, then that sends all of the points back to where they started. Okay, so now we can define what a group of symmetries is. A group of symmetries is a collection of symmetries G such that two conditions hold. Combining two symmetries in G gives another symmetry in G. And we also want inverses of symmetries in G to be in G. So we can say that G is closed under combining symmetries and it's closed under taking inverses. So sticking with the example of the square, let's see some groups of symmetries. Well, we could certainly take all 8 symmetries of the square. This is always true. If you take all of the symmetries of a shape, then that will be a group of symmetries. Or we could just take the 4 rotations. Certainly combining rotations gives you another rotation. Another example, with just 2 symmetries, we can take a reflection in the vertical axis, say, and the identity. This is a group of symmetries because performing the reflection twice will give you the identity. You can also just take the identity by itself, which is kind of a dumb example, but it is still an example. Let's now move on to another example, the square tiling of the plane. You need to imagine that this square tiling extends out infinitely in all directions to cover the entire plane. I've just drawn a finite section of it here. Okay, so what symmetries are there of this tiling? Well, there are rotations. We can pick a vertex in the tiling and perform a rotation like this, so that the grid lines up with itself again. There are also translations, where we move it like this. In that case, we've moved it 1 to the right and 3 down. Okay, now I have some questions for you. What are some other examples of symmetries of the square tiling, and how many symmetries fix the highlighted vertex? If you'd like to have a go at answering these questions, then please pause the video and spend maybe 3 or 4 minutes thinking about them, or perhaps drawing on with pen and paper if you find that helpful. Welcome back. So, what are some other symmetries? Well, there are also some reflections. For instance, you can reflect in a number of horizontal axes, like this. And of course, there are lots of combinations of the above 3 types of symmetries. In fact, this gives you all of the symmetries of the plane. Any symmetry of the plane can be constructed by first rotating and reflecting and then performing a translation. And as for the other question, how many symmetries fix the highlighted vertex? The answer there is 8. These consist of 4 rotations and 4 reflections. And these form a group of symmetries because combining 2 symmetries that fix the highlighted vertex will give you another symmetry that fixes the highlighted vertex. Note that this group of symmetries is essentially the same as the group of symmetries for the square that we saw earlier. This sort of thing happens a lot, where you see essentially the same group of symmetries occurring for different shapes. Another example of a group of symmetries here is that which consists of all of the translations of the tiling. And this is an infinite group of symmetries because you can move the highlighted vertex to any other vertex within the square tiling. And on to a third example, the 3 regular tree. So this is an infinite tree in which every vertex meets exactly 3 edges. So it will start branching out as I've drawn, and then it will continue branching out infinitely in all directions. Okay, so what symmetries are there? Well, there are things which I will call branch swaps, which are a bit like reflections, except that they don't reflect the whole tree. Let's see what these look like. There we go, something like that. So you're sort of swapping the branches that go out to the left and the branches that go out to the right in this picture. Now another question for you guys. What other symmetries of the three regular tree can you find, and how many symmetries fix the central vertex as I've drawn it here? If you'd like to answer this question, you can spend 3 or 4 minutes thinking about it, or perhaps drawing some pictures on paper if you find that helpful. So what other symmetries are there? Well, there will also be some rotations. For instance, a rotation by a third turn about the central vertex. And then there really are many, many other symmetries. We'll see some other examples in a minute. But I'd like to stress that the three regular tree is really very rich in symmetries, much more so than the previous two examples. In fact, it's quite difficult to describe every symmetry of the tree. And to touch on the second part of the question, how many symmetries fix the central vertex? Well, there are infinitely many, and to see this, we can consider an infinite family of branch swaps. So we can do this by considering a finite path that goes out from the central vertex, such as the path highlighted here in red, and we can perform a branch swap at the end of this path. So something like that, that swaps those two edges, and of course swaps all of the other branches that come off of those two edges. Of course, there are infinitely many such paths that we could have chosen, and so this gives you infinitely many branch swaps, which all fix the central vertex. And again, the symmetries that fix the central vertex form a group of symmetries, but unlike in the case of the square tiling of the plane, this is now an infinite group of symmetries that fixes the vertex. And now to talk about another type of symmetry of the tree, which touches on some of my research as a PhD student. So there's another symmetry of the tree which looks a bit like a translation. In order to see this symmetry, you have to draw the tree in a slightly different way, as I've done here. So I've drawn it so that it has an infinite vertical line, and then infinitely many subtrees that branch off to the left. But this really is still the same tree. It still has the property that every vertex meets exactly 3 edges. All I've done is kind of change the way I've drawn it. I've changed the angles and lengths of the edges, but we still consider this to be the same shape. And what does this translation-like symmetry do? Well, it does this. It shifts all of these subtrees down by 1. So very roughly, the way this touches on my research is that I'm interested in infinite groups of symmetries of this tree and of similar trees. And I'm interested in groups that consist entirely of these translation-like symmetries. And it turns out there are really many, infinitely many groups of symmetries like this. And I'm interested in the way these different groups interact within the group of all symmetries of the tree. And now to talk a bit about some other ways that groups can arise. So that the notion of groups of symmetries that I've been talking about can actually be generalized to a more abstract notion of group. I won't give the precise definition, but roughly what's going on is that a group is a collection of things with some way of combining the things together to produce a third thing, just as we combined a pair of symmetries to produce a third symmetry. And then there are some rules that need to be satisfied that make it behave similar to a group of symmetries. So this is something you would come across in the first year of a mathematics degree. And with this more general notion, you can see many settings in which these groups occur. So, for example, you can have groups of numbers where the method for combining numbers could be addition or it could be multiplication. You can also have groups of matrices where you can combine matrices using matrix multiplication. There are also groups that come up in chemistry. For example, you can have symmetries of different molecules or lattices within a metal. So this example really is groups of symmetries, as we've been studying. Groups also come up in physics. For example, there's something called the Lorentz group, which describes the symmetries of space-time in Einstein's theory of special relativity. So groups and groups of symmetries really do come up all over mathematics and the mathematical sciences. It's a very fundamental and powerful notion. And a couple of further resources. There's a video on YouTube which introduces the notion of an abstract group with some examples. There are also some notes from the Open University about groups and symmetries with lots of exercises. Thanks for listening.